All right, we're going to go through homework. I'm going to start in chapter 19. All right, 1914, balance the oxidation reduction. (1940). All right, so we got Hg2 plus 2 plus H2S. Goes to Hg plus S8. All right, so step one, you get your oxidation numbers. So you need your oxidation number for Hg on this side. You need your oxidation, we'll give them for both the H and the S, and Hg on this side and the S on this side. All right, so when you have Hg2 plus 2, that means each of those Hgs would be plus 1. H2S, hydrogen is always plus 1 unless it is a metal hydride. All right, so you got your plus 1. There's 2 of them. That makes your S a minus 2. This is Hg, mercury. It is a liquid metal at 25 degrees Celsius, so it has 0. It is in its natural state. Same with S8. All 8 of those sulfurs are 0. It is sulfur in its natural state on the periodic table. All right, so we will break into 2 half reactions. We see that our Hg2 plus 2 is going to go to Hg. All right, and our plus 1 is reduced to 0. So this is the reduction half reaction. All right, and so then our H2S is going to S8, and that is our oxidation. It increased oxidation number from minus 2 to 0. So this is your oxidation half reaction. All right, so this one is a difficult oxidation reduction because you have to do the next step, which is to balance the atom changing oxidation state. All right, so it is the Hg. We have Hg2, but we only have one Hg on this side. So you have to put a 2 in front of the Hg here. All right, and you see that when we're going from this Hg that is plus 1 over to this Hg that is 0, we have to gain 1 electron for each Hg. All right, and so we have to gain then a total of 2 electrons because we have to multiply it by the 2 Hg atoms. All right, so we have 2 Hg's on both sides, so we need 2 electrons to balance that oxidation number. Same thing here. We've got S at minus 2, but we have 8 S's at 0. So you must put the coefficient of 8 in front of the H2S. And so here we see that we have a minus 2s going to a 0s. That means we had to lose 2 electrons per s, but we see that we have 8 s's. So multiply that by 8, and that means you lose 16 electrons total. So instead of putting a minus electrons, I put 16 electrons are released. All right, so you're plus 16 electrons. All right, so now we have our half reactions and the oxidation numbers have been balanced. All right, so now I balance the charge, and in 1940, this one says acid, so that is important because when we're going to balance the charge in acid, we use H+. All right, so on the first one, we got minus 2, we got plus 2, we got 0, and on the other side, 0. That already has a balanced charge. Down here, on the left side, H2S has no charge. 0 times 8, that's still a 0. S8 has no charge, that's a 0, but you have minus 16 for your 16 electrons. And so you have to add 16 H pluses in order to get a plus 16 and a minus 16 to be a 0 on the left and a 0 on the right. All right, and so then the final is to balance any hydrogens and oxygens with water. The top one, no hydrogens or oxygens. The bottom one, we have 16 hydrogens and we have 16 hydrogens. We have no oxygens, we have no oxygens. So in this oxidation reduction, it was not required to put any waters in on either reaction, the reduction or the oxidation. All right, so now when we add them up, we have to make sure that electrons gained equal electrons lost. And so we have 16 electrons lost. In order to get 16 electrons gained, we have to multiply that through by 8. And so now we have 16 electrons, we have 8 Hg2s, and we have 16 Hgs. And so we subtract the 16 electrons from both sides. Electrons will never show up in the overall reaction. And then we just bring the things down. We have 8 Hg2 plus 2s. We have 8 H2S. That gives us 16 Hgs plus S8 plus 16 H plus. And when we check our charge, we have 8 times 2 is plus 16 and 0 here. So the total is 16. Here we have 0, here we have 0, here we have plus 16. So there is your balanced oxidation reduction half reaction, or full reaction. So going back to the half reactions, it didn't say to, but I'm going to. You have your reduction half reaction. All right, and so again, it's your reactants that are going to be your agents. And so the reactant of your reduction half reaction, that is your oxidizing agent. So this Hg2 plus 2, not Hg, that's over here. That is not the answer. Your Hg2 plus 2, this is your oxidizing agent. All right, and so if we were looking to oxidize our H2S, yes, we would add Hg2 plus 2. If we were looking to reduce our Hg2 plus 2, we would add a reducing agent. The H2S is your reducing agent. It is the reactant of your oxidation half reaction. That is your reducing agent because it will reduce the Hg2 plus 2 down to Hg. All right, I'll do one more on that one, and then we'll go to the next type of question, although the next type of question is the same question. All right, yeah, we'll do, that was A, we'll do B. So in B, you got S minus 2 plus I2 going to SO4 minus 2 and an I minus. All right. So you again have to do your oxidations. You got to have the oxidation of S, I, S. You can do O and I. All right. So a monatomic ion is simply the charge of that ion, minus 2. Iodine, element, periodic table, natural state, 0 is the oxidation number. Oxygen is minus 2 unless it is a peroxide. So this is a minus 2 oxygen. And so we have 4 of them. So that's minus 8. We have to have a plus 6 for our sulfur. We add that to the minus 8 to give the overall charge of minus 2. And your I minus, that is a monatomic ion. That is just the oxidation number is the charge of that monatomic ion. All right, so we see that our sulfur is going from a minus 2 to a plus 6. So that is your oxidation half reaction. So S minus 2 is increasing oxidation to SO4 minus 2. All right, and so we see that we would have to lose 8 electrons per sulfur. And this is where you have to be careful. You'll see a 2 and you'll see a 6 and you're going to put a 4. That is the wrong number. It is an 8. You have to lose 8 minuses for a minus 2 to be a plus 6. All right, and so here we have our iodine. So we have I2 going to I minus, all right, and so here we had to gain 1 electron per I, and note that we have I2 on this side. We have to balance the atom being oxidized or changing oxidation number. All right, and so our -2 to +6, that is an oxidation. So here's your oxidation half reaction. Your 0 being reduced to -1, that is your reduction half reaction. All right, and so now we know that the S -2, you can go up to the original problem. So that is the reactant of your oxidation half reaction. That makes this your reducing agent. It is called that because we added that in order to reduce our iodine. And the iodine is the oxidizing agent because that is what we used to oxidize our S -2. All right, so with our sulfur, we needed to lose 8 electrons per S. There's 1 S on this side, there's 1 S on that side. We had to lose 8 electrons. The iodine, we had to gain 1 electron per I. There are 2 I's, so we had to gain 2 electrons. All right, so now we have this reaction. It says it's in base. So it is basic. What does that mean? That means that we're going to balance our charge with OH minus. All right, so we have to do our charge. On the left here, we have an S -2, so that's -2. On the right, we have SO4 -2 plus another 8 electrons, another -8. And so on this side, we have -2. On this side, we have -10. We have to add 8 OH minuses in order to have a -10 on the left and a -10 on the right. We go down to our iodine, we have a -2, a 0, and a -2. So we have -2 is equal to -2. That one is balanced. All right, so after we balance the charge, we balance our hydrogens and oxygens with water. All right, so here we have 8 OH minuses. That means we have 8 hydrogens, which means we will need 4 H2Os, and that will give us 8 hydrogens. So now we check our oxygens. We have 8 OH minuses, so that's 8 oxygens. We have an SO4, that's 4 oxygens. We have 4 H2Os, that's 4 more. We have a balanced oxidation half reactions. There are no H's or O's in our iodine half reaction, reduction half reaction. So now we're ready to add them up. But again, you have to have electrons gained equal electrons lost. We have lost 8 electrons. In order to get our electrons gained to be equal to 8, we multiply that through by 4. And so now when we multiply it through by 4, we have 8 electrons, not 2. We have 4 I2s, and we have 8 I minuses. And so we have to subtract our 8 electrons from both sides. The overall reaction cannot have electrons in it. All right, so we just bring it down. We have 8 OH minuses. We have an S -2. We have 4 I2s. We have an SO4 -2. We've got 8 I minuses. And we've got 4 H2Os in our final oxidation reduction reaction. All right, so we'll check the charge, -8, -2, so that's -10 on this side, because that's 0. We got -2, we got -8, we have 0, so again, we have -10 on the left and the right. That is our balanced oxidation reduction reaction. All right, I'll go to 42 and do 2 of those as well. 42 is the same question. 19.42, balance the oxidation reduction. All right, so we have our Cr2O7 -2 plus H2O2. goes to Cr plus 3 and O2. All right, so we need our oxidation numbers. We need Cr, we need O, we need H, we need O, we need Cr, we need O. All right, so oxygen is always -2 unless it is a peroxide. This is not a peroxide, so you have a -2. There are 7 of them. That makes it -14 total. So the 2 CRs have to be a +12 in order for +12 and -14 to equal -2, the overall charge. All right, so just like 7 oxygens is -14, so each one is -2. 2 chromiums is +12, so each one is a +6. Hydrogen is always +1 unless it is a metal hydride. This is not a metal hydride. The hydrogen is +1. All right, your oxygen is -2 unless it is a peroxide. This is a peroxide where it is -1. All right, your monatomic ion, your oxidation is the charge, +3. Oxygen, element in its natural state, has an oxidation number of 0. All right, so we see that our chromium is going from a +6 down to a +3. It is being reduced from a 6 to a 3. And so our Cr2O7 2 going to Cr plus 3, that is our reduction half reaction. All right, and so we see that we are going to gain 3 electrons per Cr. All right, when we look at our oxygen, we have our peroxide that is going from an oxygen that is a -1 to an oxygen that is 0. So it is increasing oxidation number from a 1 to a 0. And so that is your oxidation half reaction, your H2O2 going to O2. That is your oxidation half reaction. And so this one, we're losing 1 electron per O. All right, so we have to make sure that we have the same number of atoms changing oxidation number on both sides. So we have 2 CRs here. We need 2 Cr plus 3s. And so when we have our electrons that say 3 electrons per Cr, we now know that we have 2 Cr atoms. And so now we have to gain a total of 6 electrons. And so we have to gain 6 electrons. Down here we have oxygen, and it says that we are going to lose 1 electron per O. But notice that we have 2 oxygens on the left, and we have 2 oxygens on the right. They are balanced. We lose 1 electron per O. We have 2 O's, and so we're losing 2 electrons. And so we put 2 electrons being lost. All right, so now we have balanced our oxidation numbers using electrons. All right, so now we got to balance the charge. So the problem says that we are in acid. And so the problem will tell you that, in acid or acidic. All right, that means that we are balancing the charge with H+. All right, so on the reduction half reaction, we got -6 here, we got -2 here, we got a -8 on the left. On the right, we have +6. All right, so when you see an 8 and a 6, you think 2. That is not the right number. All right, so you got your -8. You have to get it to be +6. All right, so you have to add 8 hydrogens just to make it neutral, 8 H pluses, and then you need 6 more. So that is +14 H plus. So -8 plus 14 is equal to 6. And so now your +6 is equal to your +6. On the oxidation half reaction, no charge on the left. You got 0 for your O2, but you got -2 for your 2 electrons. And so you have to add 2 H pluses to get a 0 on the left and a 0 on the right. All right, so now we have balanced our charge. Now we are going to add hydrogens and oxygens to balance with water. All right, so we just added our 14 H pluses here. So we're going to need 7 H2Os. That's 14 H's on both sides. All right, so now we have 7 O's, and on this side we have Cr2O7, and that is our 7 O's on the left. It is balanced. All right, hydrogens on the bottom one, oxidation, 2 hydrogens on this side, 2 on this side, 2 oxygens on this side, 2 on, all right, all the hydrogens and oxygens are balanced. Now we add up the 2 half reactions. Yep, go back and do that. All right, add up the 2 half reactions. Make sure that your electrons gain equal electrons lost. We have 6 electrons gained. We only have 2 electrons lost. And so we have to multiply our oxidation half reaction by 3 in order to lose 6 electrons as well as gain our 6 electrons. So we have a 3 there. We're going to have a 3 here. We're going to have a 6 electrons here. We're going to have a 6 H plus there. All right, and so we subtract 6 electrons from both sides. The 6 electrons gained equals 6 electrons lost. They cannot show up in the overall reaction. H plus is on both sides. You cannot have H plus on both sides of a balanced chemical reaction. You have to subtract 6 H pluses from both sides. So the right side is gone. No H pluses left. When we subtracted 6, we still have 8 H pluses left on the left side. So now we're ready to bring everything down. We've got our Cr2O7 minus 2 plus our 3 H2O2 plus 8 H plus on the left, yielding 2 Cr plus 3s and 3 O2s and 7 H2Os. All right, and so we wanted to check our charge on both sides, make sure we have the same charge. All right, so we have our minus 2, we got our 0, we got our plus 8. So we have a total of plus 6 on the left side. We have 2 Cr plus 3s, plus 6, oxygen 0, water 0, plus 6 is equal to plus 6. And so you have a balanced oxidation reduction reaction. All right, and so again, your reactant of your reduction half reaction is your oxidizing agent. All right, so here is your oxidizing agent. The reactant of your oxidation half reaction is your reducing agent, H2O2. That is your reducing agent. All right, so again, if you wanted to reduce Cr2O7 minus 2 into a Cr plus 3, you would add H2O2, the reducing agent. All right, one more oxidation reduction I'm going to do, 42B. And that is Cn minus plus MnO4 minus goes to CnO minus plus MnO2. All right, so this is a interesting oxidation reduction question. All right, so what I'm going to do is I'm going to leave Cn together. I'm not going to break it apart. You can do it different and it would still work out the same, but the easiest way to do it is I'm going to leave Cn together. I'm not going to get a separate oxidation for each one. You could. I'm not going to. All right, so you have your Cn, that's minus. All right, and so I'm going to leave Cn together and make that a minus 1. All right, so then I'm going to have my MnO4, Mn, and O, and then I'm going to leave my Cn together, and then my O, and then Mn, and then O. You could do it a different way if you wanted. I'm going to leave my Cn together. My O is minus 2, so that's minus 8. My Mn is plus 7. All right, I'm going to say that my Cn is minus 1 on this side, but I know that my O here is not a peroxide, so this is a minus 2. So now I know that my Cn has to be a plus 1. And here your O is minus 2, that's minus 4, so Mn is a plus 4. All right, so I see that my CN is going to increase oxidation number from a -1 to a +1. So I need to lose 2 electrons per CN. My Mn is going from a +4 down to a +3. That is a reduction. I have to gain 3 electrons per Mn. All right, so there's your two half reactions. You have your Cn minus going to CNO minus. All right, so that is your oxidation half reaction. All right, and then you have your MnO4 minus going to MnO2. And that is your reduction half reaction. All right, and so Cn, we have 1 Cn on this side, 1 Cn on that side, so we have to lose 2 electrons. So we are going to lose 2 electrons to balance the oxidation numbers. For our Mn going to MnO2, there's 1 Mn on this side, 1 on that side. We have to gain 3 electrons per Mn in order to balance our oxidation numbers. All right, and then this one says that we are in base. So it says basic. That means OH minus to balance our charge. All right, Cn minus, that's -1. CNO minus, that's also -1, and -2 for your 2 electrons. All right, so you have to add 2 OH minuses in order to get a -3 on the left equal to a -3 on the right. On the reduction half reaction, we've got a -1 and a -3. And on the other side, we do not have a charge. So you've got your -1, you've got your -3, that's a total of -4. Right now, that is 0. To balance that, you need 4 OH minuses for a -4 to equal a -4. Now you balance your hydrogens and oxygens with water. So your oxidation half reaction, you got 2 H's, 2 OH minuses, that's 2 H's. And so you need 1 H2O to get 2 hydrogens on both sides. Check your oxygens. You have 2 oxygens from your 2 OH minuses. You have 1 O from your CNO, and you have 1 O from your H2O. You have 2 oxygens on both sides. You have a balanced oxidation half reaction. All right, hydrogens. No hydrogens on the left. You have 4 hydrogens on the right from your 4 OH minuses, which means you need 2 H2Os. That's 4 hydrogens and 4 hydrogens. Check your oxygens. MnO4, that's 4 oxygens. 2 waters, that's 2 more. You got 6 oxygens on the left. On the right, you got 2 from your MnO2 and 4 from your 4 OH minuses. So that's 6 O's on both sides. All right, so you have now a balanced oxidation half reaction and a balanced reduction half reaction. So we're going to add them up. But again, before you add them up, you have to make sure that you have the same number of electrons gained as lost. This time we have to multiply both reactions because we have 2 and 3. The least common multiple is 6. So I'm going to multiply this through by 3. All right, so 3 Cn minus, 6 OH minus, 3 CNO minus, 6 electrons, and 3 H2Os. I'm going to multiply this one through by 2, and I will have 2 MnO4 minuses. I will have 6 electrons. I will have 4 waters, 2 MnO2s, and 8 OH minuses. So now I subtract the 6 electrons on both sides. So the 6 electrons are gone. All right, I also see I have OH on the left and I have OH on the right. You can only have OH on one side of the reaction. So the lowest number is 6. So I subtract 6 OH minuses from both sides. So now we are down to 2 OH minuses on the right. Waters are also on both sides of the reaction. We have 4 waters on this side. We have 3 on this side. The lower number is, of course, 3. I'm going to subtract 3 waters. And now I'm down to 1 water on the left. I'll make that thing disappear. All right, so 1 left on here. All right, so you bring it down. You have your 3 Cn minus. You have your 2 MnO4 minus. You have your 1 H2O on the left. All your OHs have been subtracted on the left side. You have 3 CnO minus. You have 2 MnO2s. Your waters have been all subtracted. You have 2 OH minuses. So you check your charge. You got a -3, you got a -2, you got a 0, you got -5 on the left. You got a -3, you got a 0, you got a -2, you got a -5 on the right. There is your balanced oxidation reduction reaction. All right, so your oxidation half reaction, the reactant there is your Cn minus. This is your reducing agent. Your reduction half reaction, the reactant is MnO4 minus. That is your oxidizing agent. Remember, the agents are always the reactants. All right, so let's go do a different type of problem. We'll go down to 1944. All right, half cells were made from nickel rod dipping into nickel sulfate solution and silver into silver nitrate. Here's 2 half reactions. All right, so you've got your Ag plus 1 electron going to Ag. And you got your Ni solid, and that's of course solid. Ni solid going to Ni plus 2 electrons. All right, so we see that we have a silver that's going from a +1 down to a 0. It is reduced down to 0. This is your reduction half reaction. Your nickel is going from 0 to +2. This is your oxidation half reaction. And of course, you have a red cat. What does that mean? You have reduction at the cathode. So the silver is being reduced at the cathode. All right, and so you have a cathode, you have an anode. So oxidation is at the anode. All right, so that is always the case. Oxidation, anode. Reduction, cathode. When you are drawing your cells, all right, you draw a beaker, you draw another beaker, and it's always alphabetical order. Here's your anode. Here's your cathode. All right, you're going to need a salt bridge. So here is a salt bridge. You're going to need an electrode, a piece of metal to connect to. You're going to need another electrode to connect your other metal to. All right, so we see that the anode, that is the oxidation, this is your nickel solid, and this is your nickel solution. All right, your cathode is the silver, and so your silver plus in solution here, and this is your silver electrode. All right, and then you hook your alligator clips to this. You got your voltmeter. Or your multimeter, checking the voltage. You connect it to both electrodes. All right, so does it matter what you use for the salt bridge? I'm going to use KCl. So my salt is going to be KCl. And so we see what's happening. What's happening is when this reaction is going, my Ag plus is forming Ag solid. And so over time, you're going to see silver growing on this electrode. So the Ag plus is going to turn into Ag solid, more solid metal on this electrode. So Ag plus is leaving. All right, to neutralize that, you have to add some more K plus to neutralize your electrons. So your electrons are flowing from anode to cathode. So the electrons are coming this way. Electrons are coming this way. So electrons are going into the cathode. And so the electron is reacting with the silver solution to form the silver metal. So the Ag plus is going out of the solution, and so it's building up a large negative charge because your silver was made with silver nitrate. The NO3 minus is still there. The Ag is going to Ag0. And so that means that going this way is always going to be your positive ion. And so your salt bridge is neutralizing your charge. Make sure there's not a buildup of charge. So the K plus is going to go this way. What's happening on the other side? Well, on the other side, we're eating away at our nickel. Our nickel is being eaten away. It is disappearing. And it is forming nickel plus 2. So we're building up a whole bunch of nickel plus 2. So what happens here? Well, the Cl minus is coming this way to neutralize that buildup of nickel plus 2. All right, so that's how the salt bridge is working. Then you're going to read your voltmeter. Well, then you got to go to table 19.1 and find your electrode potentials. So the reduction, and that's what it is a reduction potential. And so everything on table 19.1 is a reduction. So I find the Ag plus going to Ag, and on table 19.1, that is a 0.80 volts. All right, then I look for the reduction of nickel. I can't find the oxidation. This is a reduction potential, so I'm looking for the nickel plus 2 going to nickel solid. I see that. All right, and so the reduction of the nickel plus 2 going to nickel is a negative 0.23. I want the oxidation, I want the reverse reaction, and so that E value is a positive 0.23. All right, and so when I add up those two reactions, first thing I have to do is I have to multiply the first one by 2. Because I have to have 2 electrons gained and 2 electrons lost. The key here is I do not multiply the E value. Never multiply your E values. All right, and so I have 2 Ag plus nickel solid going to 2 Ag solid plus nickel plus 2. And the E value, so that is the E naught cell, all right, so the overall reaction is the cell reaction. We just add those up, 0.8, 0.23, 1.03 volts. So if we had our standard conditions, which means that all of our concentrations are 1 molar, our voltmeter should read 1.03 volts when you hook that up to your voltmeter. All right, so there is the cell, here is the reading, and you also know that you have a spontaneous reaction. All right, because anytime your E value is positive, you have a spontaneous reaction because delta G is equal to negative NFE. All right, and so the N is the number of electrons transferred. That is 2 electrons gained and lost. F is a constant that will be given. That is 9.65 times 10 to the 4th coulombs per mole of electron. and that's what these 2 mole of electron is. That cancels. And then your voltage is 1.03 volts. And a joule is equal to a coulomb times a volt. And so when you cancel out your coulomb and your volt, you get a joule, which is the units for delta G. All right, and so if your E value is positive, that makes your delta G value negative. And so delta G is always negative if your E is positive. That number, when you multiply that together, is negative 3 sig figs, 1.99 times 10 to the 5th joules. All right, and so we know negative delta G, that is spontaneous. All right, and so anytime you have a positive E value, we now know that that is going to always be spontaneous. We also know that a spontaneous cell is called a galvanic cell, also called a voltaic cell. All right, so that means that your E value, your E cell is positive. That means that it is a spontaneous reaction. All right, we can calculate the equilibrium constant. So delta G is equal to negative RT ln KEQ. So we just plug in our numbers. Negative 1.99 times 10 to the 5th is joules, is equal to negative 8.314, 298 Kelvin. That's joules per mole Kelvin. Ln KEQ. All right, so we plug that in. So I have my number, and I'm going to take that and divide by negative 8.314 and divide that by 298. And that's going to give me 80.2. And that's equal to the ln of KEQ. And then I take my E to the X. And I get a spontaneous reaction is going to have a very large K value. And it is. KEQ is equal to 7.01 times 10 to the 34th. All right, and so the next question can be if the concentration of nickel plus 2 is equal to 0.25 molar at equilibrium. Calculate the concentration of Ag plus at equilibrium. All right, so you have to know the setup. You got your KEQ, you go back to your overall reaction. All right, and of course, KEQ is concentration of products over reactants. Don't forget that they are raised to their coefficient. So your setup for KEQ is your product, nickel plus 2 concentration, over your Ag plus raised to its coefficient of 2. All right, and so now you have 7.01 times 10 to the 34th is equal to your nickel, which is a 0.25 molar, divided by your Ag plus squared. All right, so now you got to multiply both sides by Ag plus squared. Then divide both sides by 7.01 times 10 to the 34. All right, and so now you take your 0.25, divide by your KEQ, the 7.01 times 10 to the 34th. All right, and so when you do that, you get a very small number that is 3.56 times 10 to the negative 36. All right, and we want the square root of that to get our answer. And so if at equilibrium we had a 0.25 molar nickel, our Ag plus concentration would equal 1.89 times 10 to the minus 18. All right, and so this reaction goes to completion. That is essentially zero. That is 0.1700189 for your Ag plus. So your spontaneous reactions go to the right until essentially all of your reactants are gone. All right, we will continue doing homework, and I will post some of these as well.